Hello everyone and welcome back. So in the previous lecture we have discussed about vertex degrees, we have talked about the minimum and maximum degrees of the graph as a whole, and we have also discussed some particular types of graphs like regular graph, trivial and null graphs. In today's lecture we will be dealing with some very important topics of graph theory. The first one being complete graph, and then we will talk about complement of a graph and how to determine the same. So let's start today's lesson with a very important topic, that is complete graph. Now, why do we call it a complete graph? The complete graph is called complete in a certain sense that we cannot insert any more edges in the graph. In that particular way we call it complete. So when is it possible for us to not insert any more edge in the graph? When only we are dealing with simple graphs. So that is the key point that one should mention in the definition of a complete graph, that it has to be a simple graph first of all. So it is called complete in the sense that the number of edges in the graph is complete. There cannot be any more edge in the graph. In what sense can we say that the number of edges in the graph are complete or we cannot insert any more edge? This is possible when every vertex of the graph has been made adjacent to all the remaining vertices of the graph. If we make one vertex adjacent to all the other vertices and likewise we do so for all the other vertices also, we will find that we cannot insert any more edge in that graph. We will definitely see this with some examples. So to summarize, we define a complete graph as a simple graph in which every vertex is adjacent to every other vertex in the graph. That is, there is a direct edge between every pair of vertices in a complete graph. So the key point that we should mention in the definition of a complete graph is complete graph is a simple graph. That is very important, in which every pair of vertices are adjacent. How do we represent a complete graph? We represent it by the capital letter K. In the subscript we write the order of the graph. So if we are willing to draw K3, how can we draw K3? 3 indicates the order of the graph. So we need 3 vertices in our graph, and it is K3 means it is the complete graph of order 3. How to make this graph complete? We draw edges for every pair of vertices. So suppose we have V1, V2 and V3 as my vertices. So for this pair V1, V2 we draw an edge, for V1, V3 we draw an edge, and for V2, V3 also we draw an edge. See, now there is no possibility of inserting any more edge in this graph, with the restriction that the graph has to be simple. So if it has to be simple, we cannot insert any more edge here. So that is what is called a complete graph. It is complete in the sense that we cannot insert any more edge. So this is how we draw a complete graph. We draw the number of vertices as we require, and then we make every pair of vertices adjacent. So let's practice drawing the complete graphs. Now complete graph starts with K1, which is nothing but our trivial graph with only one isolated vertex. Why is it complete? Because here we are not having any pair of vertices, there is only one single vertex, and how can it be made adjacent to itself when it has to be a simple graph? So for that reason K1 is by default a complete graph, as it does not dissatisfy our definition of being a complete graph. Next complete graph is K2, of course, which is of order 2. So make the order of the graph 2 and make it complete by drawing an edge between the pair of vertices that you can see. Then we have drawn K3. Now let's draw K4. So we have 4 vertices, and that is the order of the graph. How to make it complete? See the technique. Choose a vertex, make it adjacent to all the other vertices. Then move to the next vertex, make it adjacent to all the other vertices. Now when a pair of vertices are already made adjacent, don't try to make them adjacent again by a multiple edge, because the graph is simple, we cannot draw multiple edges here. Now for this vertex, we make it adjacent to the remaining, and automatically this vertex becomes adjacent to all the other vertices. This is how we draw a complete graph. Let's draw K5 very carefully. So the order is 5. We should have 5 vertices in our graph. It is K5, that is a complete graph of order 5. So choose one vertex, make it adjacent to every other vertex in the graph. Then choose the next vertex, make it adjacent to every vertex. So basically what we are doing is we are drawing an edge between every pair of vertices that we can have. So my suggestion would be, pick a vertex, make that vertex adjacent to all the other, then move to the next vertex, make it adjacent to all the other. Like this, one by one you move to each of the vertices, and that is how you complete your complete graph. Okay, so let's see the definition. Complete graph is a simple graph, very important, in which every vertex is adjacent to every other vertex. It is denoted by Kn, where n is the order of the graph. We have K1, the very first complete graph, then K2, K3, and these are the complete graphs of order 4 and 5 respectively. So if we ask you to draw, suppose K7, you can draw K7 very easily, but very carefully. Draw 7 vertices, 1, 2, 3, 4, 5, 6, 7. Pick a vertex. So let's label them V1, V2, V3, V4, V5, V6 and V7. Make V1 adjacent to V2, V3, V4, V5, V6 and V7. Then move to V2 after you are done with V1. Then V2 is already made adjacent to V1, so don't draw another adjacency by multiple edges. Make V2 adjacent to V3, V4, V5, V6 and V7. In this way, now move your focus to V3 and complete its adjacency with all the vertices. Then move to V4. See, in this situation you will not be avoiding any edge, you will definitely draw all the edges that are required. So this is our K7. Now some key points that I should list down to remember while dealing with complete graphs. First point is, complete graph is simple graph. Second point is, the order of a complete graph is n. Now size of the complete graph, size of Kn, that is Ekn. Order of the complete graph Kn is nkn, that is how we denote the order, right? So what is Ekn? That is the size of a complete graph. Now whenever we deal with a complete graph, it is unique. Given a value of n, the order of the graph, the complete graph is a unique graph. So how to find out the size? There is a formula to find out the size of a complete graph. What is the formula? Now it's pure logic, as the definition goes, that every pair of vertices in a complete graph are adjacent. So as many pairs of vertices you can have, those many number of edges will be there in the complete graph. So the number of edges in a complete graph Kn will be the number of ways in which you can pick a pair of vertices from the entire vertex set. So that is what is a problem of combination. So the size is, in how many ways can you pick 2 vertices out of n vertices, that is nc2. So the formula is n into n minus 1 by 2. This is how we determine the size of any complete graph of order n. Next point is regularity. If you check carefully, every complete graph is regular. K1 is 0 regular, K2 is 1 regular, K3 is 2 regular, K4 is 3 regular, K5 is 4 regular. So basically Kn is n minus 1 regular. In Kn, every vertex has degree n minus 1. Why? Because in Kn, where you have n vertices in total, every vertex is adjacent to all the other vertices. So for each vertex, there are n minus 1 remaining vertices. So it has to be adjacent to the remaining n minus 1 vertices, making its degree n minus 1. This is true for all vertices in the graph. So Kn is a regular graph in which the degree of every vertex is n minus 1. So it is n minus 1 regular graph. These are the points that are summed up here also in this slide, as I have already discussed. Next we move to another important topic, that is complement of a graph. How to determine the complement of any simple graph. Yes, whenever we deal with complement also, we are dealing with simple graphs only, and the complement of a simple graph is also going to be a simple graph. Now if we try to bring a comparison here with complement of a set, then suppose our universal set contains the elements A, B, E, C, G, and S is a set containing the elements A, E, C. Then what is the complement of the set S? S complement, or it can be written as S complement like this, is basically the universal set minus the set S. So basically S complement is the set of all those elements of the universal set which are not present in S. So S complement contains B and G, the elements which were present in the universal set but not present in S. So that is what complement of a set is. Almost in a similar manner we can define the complement of a graph also. Now how? Now first of all we are dealing with simple graphs only here. Next, when we have a graph G, suppose the order of the graph is 3. Now the complement of the graph, which is also denoted by G bar or G, on this superscript we have C, this also has the same order. So if G has 3 vertices, G complement will also have 3 vertices. Now then what sense is it the complement? It is a complement of the graph in terms of the edges. So basically G complement, that is a complement of the graph G, will contain all those edges which are not present in G, and it will not contain any of the edges which are present in G. So of course if V1, V2, V3 are the 3 vertices, then they are the same 3 vertices in the complement also. Since V1, V2 is an edge in G, so V1, V2 will not be an edge in G complement. Since V1, V3 is an edge in G, so V1, V3 are not going to be adjacent in the complement. Since V2 and V3 do not have an edge between them in G, that is the reason V2 and V3 should have an edge between them in the complement of the graph. In the complement graph, all the vertices of G remain as it is, that is, the vertex set of the complement is the same as the vertex set of the graph itself. In terms of the edges, we see the complement nature. Now let's see another example and visualize the idea of complement of a graph. Suppose we have a graph G with 4 vertices like this. So we have U, V, W, X as our 4 vertices in the graph G. How to draw the complement? So the complement graph will also contain the same vertices. So my first suggestion would be, while drawing the complement of a graph, keep the vertices of the graph itself as it is in the same location. So we have U, V, W, X. See, I have placed the vertices in the same position as they were in the graph itself. Next, I have to deal with the edges only. So the edges that we are seeing in the graph G will definitely not be present in G complement. The edges which are not present in G are to be present in G complement. Now how to find out which edges are not present in G? So basically any pair of vertices in G which are non-adjacent must be made adjacent in G complement. See, V and W are non-adjacent in G, so V and W must have an edge between them in G complement. V and X are non-adjacent, so in complement they are adjacent. W and X are non-adjacent, so in the complement they will have an edge between them. And we will not have any more edge because any other pair of vertices are already adjacent in G, so they will be non-adjacent in G complement. Now this is a very simple graph to find the complement of. Now how to deal with this problem when we have quite a complicated graph? Now the idea is, if you carefully see the two graphs, the graph G and its complement, what we are doing, watching the graph G, we are drawing the complement such that the edges which are not in G are present in G complement. When we visualize the two graphs being merged together, we will see both of them together create the complete graph of that particular order, as many vertices the graph has. If you see this graph G, you have 4 vertices, right? In G we have these many edges. In G complement we have these many edges, right? Together they form the complete graph K4. This is what happens when we construct the complement of any graph. If we have any graph G and if we draw its complement, together they are definitely going to bring up the complete graph. So that will help us eventually to decide whether our complement is done or not. So how? So we know the order of the graph G, that is 4 here. So together they are going to give us K4. Now how many edges are there in K4? As per the formula that we have just learnt, number of edges in K4 is 4C2, that is 4 into 4 minus 1 by 2, that is 6. So there are 6 edges in the complete graph K4 that is going to be formed by the togetherness of these two graphs G and G complement. So if there are 6 edges in total, out of which 3 edges are there in the graph itself, So 6 minus 3, that is 3 edges are to be present in the complement of the graph. Now when you have carefully drawn all the 3 edges, you are sure that there is no more edge to be drawn in the complement. That is one way to cross check your answer that your complement is correct. Now make sure you definitely have not drawn any edge in the complement which is already present in G. That you have to be careful about. Keeping that in mind, you draw edge between every pair of non-adjacent vertices in your graph G, make them adjacent in G complement and see if you have reached the required number of edges, then think your complement of the graph is done. Now let's see another example. Suppose our graph G is this graph. So there are 5 vertices, say u, v, w, x, y. Order is 5. So in the complement graph also we will have the same 5 vertices. Now if you see carefully in the graph G, you will not find any pair of vertices which are non-adjacent. You will see every pair of vertices adjacent. Why? Because what I have drawn is nothing but K5. This is the complete graph of order 5. So here every pair of vertices are already adjacent and I cannot draw these edges in the complement. Now in the complement graph, I cannot draw any edge because I do not have any pair of non-adjacent vertices in our graph G. So my complement graph looks like this, that is, it is an edgeless graph. So this is something that we can conclude here, that complement of Kn is edgeless graph of order n. So if you are dealing with K2, its complement will be the edgeless graph of order 2. If you are dealing with K10, the complement of K10 would be the edgeless graph of order 10. Similarly, the other way around, if we find out the complement of edgeless graph of order n, then we will find it is Kn. So if you are having an edgeless graph of order 2, its complement is going to be K2. We will see that again as an example. Before that, let's see the definition. The complement of a simple graph G is again a simple graph denoted by G bar or G power C, in which, see, the vertex set of G complement is equal to the vertex set of G and UV will be an edge in G complement if and only if UV is not an edge in G. That is what the definition of complement is. So let's see an example where we will find out the complement of an edgeless graph. So this is an edgeless graph of order 4. What will be the complement? Same 4 vertices will be there. As we can see in the graph, no 2 vertices are adjacent. So basically in the complement, every pair of vertices should be made adjacent. In the graph, the vertices u, v, x, y are mutually non-adjacent to each other. So the same vertices in the complement will be mutually adjacent to each other. So for every pair of vertices in the complement, we draw an edge between them in a similar way as we draw the complete graphs. Okay, so the complement of a complete graph is an edgeless graph and the complement of an edgeless graph is a complete graph. Let's see some solved examples here. This is a graph where the vertices u, v, x, y are present, uv being adjacent, vx being adjacent and xy being adjacent. So in the complement, we have ux as adjacent vertices, vy are adjacent, uy are adjacent, which were non-adjacent in the graph G. So how do we cross check our answer? So this is a graph of order 4 we are talking about. So together they are going to make K4 definitely. The size of K4 would be 4C2, that is 4 into 3 by 2, that is 6. In the graph there are 3 edges already. So 6 minus 3, that is 3 edges should be present in the complement. Since we have already drawn 3 edges and we have drawn it correctly between only those non-adjacent vertex pairs of G. So this is our complement. Now next we have a very simple graph. It's basically K2 and its complement is an edgeless graph. This graph G again has 4 vertices. So together they are going to make K4. Total number of edges should be 6. Including the edges of both the graphs G and G complement, out of which 1, 2, 3, 4, 5 edges are already there in G. So 6 minus 5, that is, the complement will contain only one edge and that is the edge between the only non-adjacent pair of vertices in the graph. Here we have the graph G as K4 only. It is a complete graph of order 4, and we see its complement is an edgeless graph of order 4. Now let's see what can we have if we find out the complement of a graph. Like suppose we have a graph which looks like this, u, v, w, x, y. So the complement would be containing the same 5 vertices u, v, w, x, y. As I can see, there are 5 vertices in the graph. So G and G complement together are going to make K5. The number of edges in K5 are 5 into 5 minus 1 by 2, that is 10. In the graph there are 1, 2, 3, 4, 5 edges. So in the complement there are going to be 10 minus 5, that is 5 edges in total. Now which edges will be there? Since u and x are not adjacent in G, so there will be an edge between ux. Similarly, there will be an edge between vy. Next, u and y are non-adjacent in G, so there will be this edge between u and y. And we can see u and w are not adjacent, so we make uw adjacent in the complement. Similarly, we make y and w also adjacent in the complement. So this is the complement graph, and we can see we have drawn 1, 2, 3, 4, 5 edges as required. So this is the complement graph G bar. Now if we want to find out the complement of this complement graph G bar. Now this is the graph G bar. Our job is to find out its complement. So that graph will also have the same vertices. Now this is the original graph for us, G bar, and we are drawing its complement. So u, v, w, x, y. This is our graph G bar. Its complement will contain those edges which are not present in G bar. So G bar does not contain the edge between uv. So we draw uv. Similarly, we draw yx, we draw vx, we draw vw, and we draw xw. These are the non-adjacent pairs in G bar. So they will be present in its complement. See, we obtained it as the same graph as G. So this is basically the idea. If we find out the complement of a graph, it gives us the graph itself back again. Okay, so let's see another example for finding out the complement of a graph, just for our practice. So let's take this graph. Okay, so what will be the complement? This is u, v, x, y, z. Then we have the same vertices in the complement also. Okay, that's the complement, u, v, x, y, z. So uy should be made adjacent here, vz should be made adjacent here. What else? X is already adjacent to everyone, so x will not have any adjacency in your complement. U and z, they were non-adjacent. V and y, they were non-adjacent. Okay, that's all I can find for. Now let's check. 5 vertices are there in the graph, so together they are going to form K5. Number of edges in K5 is, we have already found out, that is 5 into 4 by 2, that is 10. The graph has 1, 2, 3, 4, 5, 6 edges. So the complement should have 10 minus 6, that is 4 edges. So I have drawn 1, 2, 3, 4, so I am done. Okay, so this is how we find out the complement of a graph. Now some important points regarding complement, that it has to be a simple graph whose complement you are finding out, and the resultant graph, that is a complement of the graph, is also a simple graph. The complement of a complete graph Kn is edgeless graph of order n. Similarly, complement of an edgeless graph of order n is the complete graph Kn, as we have discussed. Complement of a graph is the graph itself. So these are some key points that one should remember while dealing with complement of a graph. So that's all for today. Again, we are going to meet for the next lecture. Till then, if you have any queries or suggestions, please do let us know. Thanks for watching. Take care and bye-bye.